Hello, this is video 31. In this video, I'm going to go over a few examples dealing with static friction, and then an example using Newton's second law with kinetic friction. Let's start with the conceptual questions for static friction. A box on a rough surface is pulled by a horizontal rope with tension T. The box is not moving. In this situation, which is true? What's the static friction force equal to? So let's really take a look and see what we have here. The box is not moving. It does not say that the box is on the verge of slipping. So that means that all we know about that static friction force is that it's opposing that tension force with the same magnitude. So that's all we know, that the static friction force equals the tension. We cannot use the definition that the static friction force equals the static friction coefficient times the normal force, which is what choice C says, because the box is not on the verge of slipping. So we do not have maximum friction force quite yet, so we cannot say that it's answer choice C. Let's take a look at the next one. A box with a weight of 100 newtons at rest is then pulled by a 30 newton horizontal force. Does the box move? So in order for the box to move, that pulling force has to be greater than the maximum static friction force. The maximum static friction force is mu n. In this case, mu n is equal to mu mg. Again, this is not always the case, but this is the case because the normal force and the weight are the only two vertical forces, so they balance each other because we're in equilibrium in the y direction. So now we just plug in our numbers. Mu s is 0.4, and the weight, which is mg, is 100 newtons. That's the weight. So 100. So that's 40 newtons. So the pulling force does not exceed the maximum static friction force, so that means it will not get the box moving. So the answer is no. Let's take a look at one more. In general, the coefficient of static friction, how does it compare to the coefficient of kinetic friction? And this is something I mentioned in a previous video, that it's actually greater than the coefficient of kinetic friction. It's harder to get something moving than to keep it moving. That coefficient of static friction is greater. And finally, let's do one more example using Newton's second law. This example, we have a mass of 4 kilograms here, that it's attached by a rope over a pulley to a mass of 3 kilograms. And what's the acceleration of the hanging mass? And it gives you that there's friction on this surface. So we know the mass is going to accelerate downward, and one is going to accelerate to the right. Same acceleration. We're going to go ahead and set up Newton's second law for each mass separately. First, we need to draw a free body diagram. So for M1 here, we're going to, I'll draw right here as a dot. M1 has a normal force because there's a surface, has a weight that balances that normal force. And then there's a tension pulling to the right, and there's a kinetic friction force opposing that pull. And then for M2 here, we have the weight pulling it down and the tension pulling it up. All right, so now we can write Newton's second law separately for the x and y directions. So for M1, the sum of fx equals M1 times a, x, and the sum of fy equals M1 ay. But there's no acceleration the y direction. The box is not jumping up and down on the surface, so we're in equilibrium. We can cross that out to 0. Now we're ready to add up our forces. In the x direction, we have tension minus kinetic friction equals m1a, and I'm just writing ax as a because that's the only acceleration. We don't need that subscript. And then for the y direction, the normal force minus m1g, up is positive, down is negative. So that tells us that the normal force equals the weight, which we already knew because there are no other vertical forces. Now we can plug in the definition of friction force, which is mu k times n. And finally, as is often the case, we can plug in what we found for the normal force in the y direction. We can plug that in for the x direction. So we get T minus mu k m1g equals m1a. And at this point we're stuck because we don't know the tension. We're trying to find acceleration. So now we can write down Newton's second law for M2 here. So for M2, we have the sum of the forces equals M2A, and since there's only one direction, I don't have to specify X or Y, and I'm going to choose the direction of the acceleration as my positive direction. So I'm going to choose down as positive and up as negative, just my preference. So that means that the weight here, the M2G, is going to be positive, and the tension is going to be negative, and that's going to equal M2A. Again, if you don't like doing it this way, you can do T minus M2G, right? Up is positive, but then you have to make sure to put a negative in front of the acceleration since your acceleration is going down. Either way, you'll get the same exact answer. So now we have two equations and two unknowns, and the way I'd like to solve for acceleration is using the elimination method. I'm going to rewrite this first equation here, going to rearrange the terms so that we can see that the tension will cancel out. That's why I like this method for this problem. When we add up these two equations, we get negative mu k times m1g plus m2g. We're just adding up these two terms here. The tensions cancel out, so that's equal to m1a plus m2a. And you can go ahead and factor out that a. It's m1 plus m2 times a. And now you can solve for a. Just divide both sides by m1 plus m2. So we have minus mu k m1g plus m2g over m1 plus m2. And now we have to plug in all the numbers, so I'll tell you what to plug in. I don't have room to write it down though. Mu k is 0.5, m1 is 4, g is 9.8, plus 3 times 9.8 over 3 plus 4. When you do all of this, what we're going to get as our final answer, which I'll write down here, I ran out of room here, 1.4 meters per second squared. So that's the final answer. So I hope this was helpful, or just a little bit of extra practice with friction.